Hello all, uh, welcome to the course Electrical Measurements and Instrumentation. I am Dr. M. Laxmidevi, Associate Professor from the Department of Electrical and Electronics Engineering at Institute of Aeronautical Engineering. Today's topic is types of torques. We know that almost all the instruments which we are using in laboratories like voltmeter, ammeter, wattmeter, etc., they are of electromechanical type. Electromechanical in the sense the input is electrical, and the output uh, in the form of mechanical deflection of the pointer. So the quantity which is to be measured, so that it can be a current or voltage, so that is given as electrical input, and output is measured in the form of deflection of the pointer. So we have seen in the last class analog instruments, they are classified into three types: indicating, recording, and the last one is integrating instruments. So among them, indicating instruments, so these are of electromechanical type. So they indicate the value of the electrical quantity which is to be measured. So essential system of indicating instruments are, so these are the three essential torques which are essential for indicating instruments. First is deflecting torque, then controlling torque, then and the last one is damping torque. So let us see one by one what is deflecting torque, what is controlling torque, and what is damping torque. So deflecting torque, it is also called as operating torque. It is required for moving the pointer from its zero position. Uh, we know that indicating instruments, it gives the value of the quantity or magnitude of the electrical quantity which needs to be measured. So that is indicated by means of this pointer and scale arrangement. The system producing this deflecting torque is called deflecting system. Deflecting system, what it does is it converts the electrical current or potential so into a mechanical torque called as deflecting torque. The magnitude of this deflecting torque will depend upon the value of electrical quantity which needs to be measured. So it can be current or voltage which is fed to the deflecting system, and the output is in the form of mechanical torque, and that torque is called as deflecting torque. So the deflecting torque, we know that it is produced by any of the following effects which are given here. So we have discussed all these effects in the last class. Let us see once again. First one is magnetic effect. So what is magnetic effect? Magnetic effect is, so when we have necessary requirements for this magnetic effect is current carrying conductor and then magnetic field. So when these two conditions are met, so when we have a current carrying conductor which is placed in a magnetic field, so that will, the conductor will experience a force, so due to which it will move. So the conductor will move. So this effect is mostly used in instruments like moving iron instruments, um, or they are also called as MI instruments. Now, next effect is, so the other effect which is used for producing deflecting torque is thermal effect, electrostatic effect, then induction effect. So let us see thermal effect. So the current which is to be measured is passed through a small element which heats it to cause rising temperature, and this rising temperature is converted into an EMF by means of a thermocouple which is attached to it. Next is electrostatic effect. In electrostatic effect, what we have is there are two deflecting plates. There are two plates which are placed near to each other, and there will be a force exerted between them. So one of the plate is at fixed position, and the other is one is fixed and the other is movable. So these plates, this movable plate can move under the influence of the force exerting this between this fixed plate and moving plate. So this effect is mostly used in instruments like electrostatic instruments. So we have electrostatic voltmeter. Next is induction effect. So in induction effect, we have a non-magnetic conducting disc. It is placed in a magnetic field. So there will be EMF induced in the conductor, and then in induced there will be currents induced in the there are eddy currents induced in that conducting disk. So due to the interaction of the eddy currents and the conducting due to the interaction of the induced currents and the magnetic field, so this induced these eddy currents will oppose uh, the motion of the conductor. So that is induction effect. Next is Hall effect. So in this we have seen that if we have a bar of magnetic material, semi-conducting material, if it is placed in a magnetic field, suppose these are the magnetic field lines, then if it is a current carrying conductor, it carries current, then we know that there is a voltage induced at the two edges of the conductor. So here we have the voltage induced at the two edges of the conductor. So this effect is utilized in pointing vector meters, etc. So these are the various effects by means of which deflecting torque is produced. So let us see the instruments where these different effects are can be available or present. So first is magnetic effect. So magnetic effect, based on magnetic effect, we have ammeters, voltmeters, wattmeters, and integrating meters. Based on thermal effect, we have ammeters and voltmeters. Then based on electrostatic effect, we have only voltmeters. Then for induction effect, we have AC ammeters, voltmeters, wattmeters, and integrating meters. Then for Hall effect, we have ammeters, flux meters are there, and then pointing vector, wattmeter. So these are the different effects which we have seen. And then based on for these different effects, we have these particular instruments. Now let us see the other type of torque that is called as controlling torque. So we have seen that um, in indicating instruments, the value of the quantity which is to be measured, that is given by the uh, position of the that is given by the position of this pointer. So this is the scale. Yeah, this is the scale and this is the pointer. Um, so in the absence of controlling torque, what will happen? Let us see. So deflecting torque. So when current is supplied to the moving system, so the pointer will deflect on the scale. But in the absence of controlling torque, what will happen is this pointer will move to the at the end of the scale. This pointer will deflect uh, till the this pointer will deflect till the end of the scale or whatever the range of the instrument is. Whatever the range of the instrument is, till that end it will deflect. But this is not required. So what is to be done is we have to limit this pointer movement such that so whatever the current we need to limit the pointer movement such that uh, whatever the current or voltage which need to be measured, so based on the magnitude of that current or voltage, this pointer should deflect or it should stop at that particular position. So this torque, the torque which opposes the motion of this pointer is called as controlling torque. So let us see. This torque opposes the deflecting torque. So if deflecting torque moves the pointer in this way, the controlling torque will act in opposite direction with the same magnitude. It will increase with the increase in deflection of the moving system to limit its movement. So there are requirements of the two important requirements of controlling torque are first, in order to so in the absence of deflecting torque, this pointer should be brought back to its original position, that is zero position. So that is one of the important functionality of controlling torque. The other requirement of controlling torque is it should produce a deflection uh, such that it's the pointer, the controlling torque is required to bring the moving system back to zero in the absence of deflecting torque. This is one important requirement. The pointer is brought to rest at a position where the two opposing torques, that is deflecting and controlling torque, are equal. So this is another important property of controlling torque. Next, for the we have two types of methods: spring control and gravity control, by means of which we can produce controlling torque. So first, let us see the first one, spring control method. So this is the most common method of providing controlling torque, which is used in electrical instruments. So here you can see the arrangement. In order to produce controlling torque, we are using spiral hair springs. So what these spiral hair springs do is, when the pointer deflects under the under the influence of deflecting torque, so this the spiral spring these spiral springs, which are made up of phosphor bronze. So they are made up of phosphor bronze. So these are coiled in opposite direction to produce the required controlling torque. So to avoid temperature variations, so since these are springs, so they have effect of temperature. So to avoid temperature variations, what we do is we use two hair springs. So you can see in the diagram there are two hair springs used to avoid temperature variations on the of the spring when when the pointer moves. So one spring will be compressed while the other will be expanded. So one spring, there are two hair springs made up of phosphor bronze used. One spring will be compressed while the other will be expanded. So we can write the equation for controlling torque as, so for flat spiral spring, Tc is equal to E into B into T cube divided by 12L into theta in Newton meters. So where E is the Young's modulus and B is the Young's modulus, B is the breadth of the width of the spring, then T is the thickness of the spring. Next, after that we have L. L is the length of the spring. So based upon the spring we have taken, so EB, EB, T, and then L are constant. So these are constant. So from this we can write Tc is equal to some K into theta, where K is equal to E into B into T cube by 12 into L. So this is so from this we can say that the controlling torque is directly proportional to theta, the angle of deflection of the pointer. So this K is also called as spring constant or restoring constant, or the other name is control constant. So this K is constant for a particular type of spring. There are some important properties. So you can see here from this diagram, there are two spiral hair springs which are made up of non-magnetic alloys such as phosphor bronze. They are attached to the moving system. So when the pointer deflects, the spring is twisted in opposite direction and it provides the required controlling torque. To eliminate the effect of temperature variations upon the length of the spring, we use two springs which are coiled in opposite direction. So when the moving system deflects, one spring is extended while the other is compressed. Now, regarding the scale of spring control instruments, so here the scale for PMMC instruments, we can see that deflecting torque. So we represent the deflecting torque by T suffix small d. It is proportional to the current which is supplied to the instrument. Then for spring control instruments, we have seen that Tc is proportional to, that is controlling torque is proportional to theta. So at steady state or equilibrium, at final deflection or steady state position, so this controlling torque is equal to deflecting torque. So from these two we can write it as theta is proportional to I. So so this is an important relation. So from this we can say that the theta is proportional to the magnitude of the current. Coming to spring control systems, so we have some important properties. So there are some properties of the spring. So important properties of the spring are properties of spring. First one is it should be made of non-magnetic material. Next is it should not be subjected to fatigue. Not subjected to fatigue. Then third one is it should have low resistance for the instruments in which current is led into the system by springs. That means according to the variation of the temperature, its resistance should not vary largely. So therefore we use the springs made up of phosphor, bronze or bronze alloys. Next, coming to the advantages of this spring control system. So there are some advantages and disadvantages of using this system. So what are they? Let us see. First one is leveling of the instrument is not required. So that is one of the advantage. Leveling of the instrument. Next is gravity control. So in gravity control, what we have is there are, in addition to the balance weight, we have additional weight called as control weight. Control weights and balancing weight. Balancing weight is also available for spring control system. So additional weight we have is control weight. So in the absence of no deflection, so in the absence of deflecting torque, the pointer is at rest or at zero position, you can say, and this is the position of the control weight. It is vertical, and whenever there is a deflection of the pointer, so when there is deflection of the pointer, accordingly this control weight uh, will also change its position. So as you can see here, so it will try to restore to its original position, that is this one, which is vertically downwards. It will try to restore to its original position, this position, but because of the pointer it will be in this position. So this is the path it has to travel. So we can resolve this into two components. So this weight or control weight can be resolved into two components. So along this one is W cos theta and the other component is this one, W sin theta. So which tends to restore the control weight to its original position. So you can see here, so in this small adjustable weight is attached to the moving system in such a way that in deflection condition it produces restoring or controlling torque. So there are two weights, controlling torque W1 and other weight for balancing the weight of the pointer. So in gravity control, Tc is equal to W1 sin theta into L. So this is a component which is responsible for bringing the pointer back to its for bringing the control weight to its original position. So this is equal to, you can write it as W1 into sine theta. So from this you can write it as, where W1 and L, this is the length and this is the weight of the control weight. So these two are constants. So WC is proportional to sine theta. So in this type of instruments where gravity control is used, so we can see that controlling torque is proportional to sine theta. So if TD is proportional to I, that is reflecting torque is proportional to I. So at equilibrium position or steady state position, so TC is equal to TD. So from this we can say that I is proportional to sine theta. So these are the instruments. So in gravity control type of instruments, the scale is non-uniform. Whereas for spring control instruments, the scale is uniform. For gravity control, the scale is non-uniform. It is cramped at the lower end. So let us see some of the differences between gravity control and spring control. So in gravity control, we have adjustable weight is used, which produces the controlling torque. So in spring control, we have seen that there are two hair springs are used, which exert controlling torque. Controlling torque can be varied here, so that is one of the advantage in spring control systems, in gravity control system. Whereas in spring control, control torque is fixed. It cannot be varied. So once the system has been designed, we cannot vary the controlling torque. In this case, the scale is non-uniform, but here in spring control, the scale is uniform. The controlling torque is proportional to sine theta, and the controlling torque is here is proportional to theta. The system must be used in vertical position only. So this is one of the drawback here. So this system where gravity control is employed, it is used in vertical position only. So that means the instruments have to be wall mounted or vertically mounted. But here there are no such restrictions. The system need not necessarily be used in vertical position. So these are simple, cheap and delicate. These are simple, rigid but costlier than gravity control. So these are costlier. These are rarely used for indicating and portable instruments. Spring control method is popularly used method in most of the instruments. Now, the next type of torque which is available in indicating instruments is damping torque. So all the indicating instruments are second order systems. So we know that in second order systems, the term damping comes into picture. So because as you can see in the diagram, so this is the case of an underdamping system. So if the system is an underdamped system, you can see there are oscillations present in the system before reaching the final steady state value. Whereas for overdamped system, you can see that for overdamped system, there are no oscillations, but pointer moves very slowly to the final steady state position. Whereas you can see from here, this is the curve of critical damping. For critical damping, pointer will reach to the final value in quickest possible time without any oscillations called as deadbeat. So all the indicating instruments, they exhibit this behavior. So there are oscillations in the indicating instruments before reaching the final steady state value. So in order to avoid these oscillations, so there is a system called as damping system to provide damping torque. So damping system to provide damping torque. So in damping system, we have a damping torque can be provided by different methods. So that we will see. So damping torque, what is damping torque? It is that part of the instrument which provides damping force to damp the oscillations of the pointer before coming to rest. Because of inertia, so this damping comes into picture uh, because because of the presence of moving system. Because the pointer has some mass and inertia, so pointer of the instrument will oscillate about its final deflected position for some time before coming to rest. So this causes waste of time in taking the readings. So damping force will act as a brake to prevent the oscillations of the moving system, and it will bring the pointer back to its final deflected position quickly. So that is the main motto of providing damping torque to the system. So there are different methods of providing damping torque. First one is air friction or pneumatic damping method. Second one is fluid friction method, and the last one is eddy current damping method. So we'll see one by one. First one is air friction or pneumatic damping method. So in this you can see here, so there is a scale, this is a pointer, this is the spindle on which the moving system is, pointer is attached to the spindle, and attached to the spindle we have an arrangement. So this is the air chamber inside, this is a chamber, so where air is there, so air chamber, and this is the piston which moves in and out of this air chamber. So how this damping torque is provided, let us see. The piston moves in fixed air chamber. It is closed at one end. So as you can see here, it is closed at one end. It is closed at one end, and the other end, the piston can move in and out of the air chamber. Clearance between the piston and wall chambers is uniform and small. The piston will reciprocate in the chamber when there are oscillations. So you can see here this spindle, this piston is attached to the spindle. The spindle is attached to the pointer. So when there are oscillations in the pointer, so accordingly this piston will also reciprocate in the air chamber, or it will oscillate. Then let us see how this method provides damping torque. When piston moves into the chamber, air inside is compressed. So when it's suppose that the pointer is moving to the left, so under the influence of oscillations, if the pointer moves to the left, so what happens is, so this is connected to the, so this is connected to the, so this is the air chamber. So this is the piston, you can say. So here you have air inside it. This is the air chamber. So when this is moving to the left, when the pointer deflects towards the left, so what happens is, so this piston will move downwards. So piston will move downwards. Piston is moving downwards means volume inside. So the volume of the air inside the volume will increase, and accordingly the pressure inside the air chamber will decrease. So as pressure is decreasing inside the air chamber, so the outside pressure, that is the atmospheric pressure, will be greater than the pressure of the chamber or the air chamber. So accordingly the piston which is there, it will move, it will it will move inwards. So when the piston is moving inwards, so this pointer will move in this way towards the right. So in this way, it will provide damping torque. When piston moves into the air chamber, air inside is compressed and pressure of air developed due to friction opposes the motion of the pointer. There is also opposition to the motion of moving system when piston moves out of the chamber. Thus, the oscillations and overshoot will get reduced due to and fro motion of the piston in the chamber. This provides necessary damping torque. So this helps in settling down the pointer to its final steady state position very quickly. So this method is suitable for instruments having weak magnetic field. So example for this type of damping method is provided in MI instruments and then electrodynamometer type instruments. The next method of damping is fluid friction damping. So it is similar to air friction damping method, but here instead of air we have a liquid is used here. So that is damping oil is used here to provide the necessary damping torque. So viscosity of the fluid is used to provide the damping torque. Uh, you can see here in this diagram we have a vessel filled with oil. There is a vane or disc, and attached to this vane or disc is the spindle is attached to this, and attached to the spindle we have a pointer. So when the pointer will oscillate, so there will be oscillations in this disc also. So that means it will move, uh, it will be tilted in the it will be tilted in this way according to the oscillations of the pointer. So it will be tilted in this way. So due to the drag of the or viscosity of the fluid, there will be frictional drag. So due to which it will restore to its original position, that is this position. So in this way, this fluid friction damping works. Let us see in detail. In this method of damping, a light disc is attached to the spindle of the moving system and completely submerged in damping oil in a pot. Motion of the disc is always opposed by frictional drag on the disc. This frictional drag is zero when the disc is stationary, so that is what expected in the absence of deflecting torque. So we do not want for the damping torque to act. So there is no frictional drag. So frictional drag is 0 and damping torque is 0. When the disc is stationary, and it will increase, the frictional drag will increase with the speed of rotation of the disc. For increased damping, vanes in a vertical plane, which are carried on a spindle and immersed in oil, are used. So mostly the fluid which is used here is oil. So serves as a for oil serves as an insulator also. Fluid friction damping can also be used in instruments which are used in vertical position. So this type of damping is used where the instruments are vertically mounted. Now let us see. So this method is suitable for the instruments having low deflecting torque. So these are not portable instruments. For example, are electrostatic voltmeter. Advantages: the oil used in the fluid friction damping can be used as an insulating fluid also. That is, it also acts as a dielectric medium. Fluid friction is suitable for electrostatic type instruments. So as these instruments, they are suspended rather than pivoted. That means they are vertically mounted. Disadvantages are, since the liquid needs to be in an upright position, this method of torque can be used vertically only. So that is the main disadvantage. Keeping the instruments clean might be difficult as the leakage of oil cannot be maintained. That is another disadvantage. Next is eddy current damping. So eddy current damping is used in the instruments where we have a strong magnetic field. So requirement for this is strong magnetic field. So this type of damping has two forms. It has two forms of damping devices. First one is metal former and the second one is aluminum disc. Circular aluminum disc with damping magnets provided, moving in magnetic field. So it works on the principle that when a conducting material is placed in a magnetic field, so eddy currents are induced in such a way that there is opposition to the motion of the conductor. So this is the principle on which eddy current damping is based. So let us see these two types of damping devices. First one is metal former and then the next one is circular aluminum disc with damping magnets provided. You can see here, this is the damping magnet. This is the second type of device. Circular aluminum disc is there and we have damping magnets which are moving in magnetic field. So first one, metal former. So in metal former we have permanent magnets. There is an iron core. So above this we have an aluminum former. Over the aluminum former we have a coil. The coil is placed. So this is the coil, copper coil placed. This one is attached to the, this is moving. This coil is attached to the pointer and the pointer will show the reflection on the scale. So when current is supplied to the coil, what will happen is the coil will carry current. So when current carrying conductor is placed in magnetic field, when current carrying conductor, so that is the coil which is placed in a magnetic field, then there will be a force exerted on the coil. So associate this coil is placed in the aluminum former. So as the coil deflects under the influence of deflecting torque, the aluminum former will also rotate, or it will also try to change its position, or it will try to rotate. So because of this rotation, there are eddy currents. Since it provides a closed path, so there are eddy currents induced in the metal former, in the aluminum former. So eddy currents are induced. So this eddy currents, they oppose the cause. So the cause is nothing but the motion of the rotation of the rotation of the pointer attached to the this pointer which is attached to the coil. So thus these eddy currents will oppose the motion of the pointer. So in this way, this type of damping is provided in metal former. Then this is the other type of arrangement. In this, we can see that there is a thin disc, usually of copper or aluminium, which is mounted on the spindle. So when the disc is moving in the magnetic field of permanent magnets, so there are lines of force are cut and eddy currents are induced. So the force will exist that exists between this current and magnetic field is always in the direction opposing the motion, and thus provides the necessary damping. So it opposes the motion. This is according to Lenz's law. The magnitude of the induced current and therefore damping force, which is independent on it, is directly proportional to the velocity of the moving system. So damping, represented by dB, is proportional to velocity of the system. Whereas in case of metal former, in this method, we can see that, or we have seen that aluminum vane and permanent magnets are used. So this is effective damping method. This method is suitable for the instruments having strong magnetic field. Among the all different methods available for damping, so eddy current damping method is the most efficient one. So this method is useful where we have a strong magnetic field, whereas if the magnetic field is weak, there we can use air friction damping method. So that's all. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.